Hi, welcome to Signal Path short episode. To be honest, since I started my Patreon channel, I kind of feel bad making regular length videos because I don't want to charge my Patreon supporters too often, and I've been making a lot of videos recently. And so I've been making a lot of short episodes instead, and those are of course not charged to my Patreon account. But everything that you guys add to the Patreon support will go back to the lab, and I really do appreciate those of you who've been doing that. So today I wanted to take a look at some of these mechanical attenuators. Now these mechanical attenuators can be quite expensive and obviously range in different frequencies and different levels of attenuation. Now the reason I want to take a look at this is because these are obviously mechanical because these are not solid state, and these are fundamental building blocks for synthesizers and front end of spectrum analyzers and even network analyzers. And the reason for that is because they are extremely repeatable in measurement and also very low loss, low insertion loss, and very accurate. And that's the reason why they use them. Of course, these can handle a lot of power. They have essentially infinite linearity. So you can imagine that these are really critical components, building blocks. But because they're mechanical, they're bulky and they're pretty expensive, and they wear out because there's mechanical movement in them. They're basically a bunch of relays, some RF relays, microwave relays. And we'll take a look and see how they operate inside. Now I've taken apart a lot of microwave equipment and I fixed a whole bunch of them, and you've seen these in various applications. Now I have two of these here. Both of these are bad, as this one clearly says, and this one has the relays completely non-functional. I couldn't get any switching, and this one does switch, but it seems to be skipping one step, meaning one of the attenuators inside isn't actually working. Now all of these guys are dB linear, meaning that they're linear in dB, but which means that the attenuation itself is obviously exponential as a function, as a result of that. Now this one is rated up to 6 gigahertz and 70 dB attenuation in 10 dB steps. And this one is rated to 26.5 gigahertz, and this is 66 dB, and I couldn't figure out how many dBs, maybe 1 dB per step, 2 dB per step, I'm not quite sure yet. Maybe when we open that, we'll figure it out. Now these are always 24 volts. This is a standard that Keysight has been using for since the HP time. In fact, this is HP branded and this is Agilent branded. And if you look at these part numbers, you'll see that these can be very expensive, especially the 26.5 gigahertz one. And this is pretty obvious by immediately looking at the connectors. These are SMA connectors, so they could not possibly be rated more than 18 gigahertz because that's where the mode changes for the SMA type connector. And this is a type K connector. You can see that the dielectric is air. And I've talked about this in my microwave component tutorial video from a while back. And you can see the difference between the connectors and how they work and so on. This is where the power is applied, and these are individual wires connected to different relays, so you can switch them in and out and get the required attenuation. Now you can see that this one is significantly longer than this, means that this has more sections. These are literally made of sections, so this will have finer steps, and this one, even though it has more attenuation in total, has very coarse steps. Now how many steps? This one's supposed to be 10 dB per step, so it would have only 3 sections, a 10 dB section, a 20 dB section, a 40 dB section. And these are always binary weighted so that you can get, these linear steps depending on the minimum step you have. So anyway, enough about that. And what I wanted to do is take it apart and show you what's inside of it. Let's start with the cheaper one and the simpler one. And I'm curious to see if they use essentially the same thing in the 26.5 gigahertz version, or have they taken some care of microwave connectivity to make it even basically work at the higher frequencies, or is it just simply a matter of having a different connector? Because for them it may be cheaper to engineer one that works at much higher frequency and simply mount it with a connector that would do the job. I suspect that this is a bit more complicated than that one. Anyway, they've been manufactured quite far apart in time. There's no date on it, but given that this is Agilent, that was HP, probably at least in a couple of years apart. So let's go ahead and start taking this apart and see what happens. And you really don't need much to take this apart. These are all the same screw everywhere, so there's no shortage of screwdrivers. Now one other thing I wanted to say is that these mechanical attenuators are actually quite loud, and if you ever power on one of these instruments, you can always hear the loud clicking of the instrument as it goes through different attenuation levels. And because these attenuators can die and can age and so on, a lot of instruments actually keep track of how many times the attenuators have switched. And if you look at the system properties of, for example, some advanced spectrum analyzers, it will tell you, oh, I've switched the attenuator 21,000 times or something, because these are only rated for a certain number of switches. And after that, they are basically not in spec anymore. If they have a 0.05 dB repeatability, well, that's out the door. And the spectrum analyzers repeatedly switch these if they're left running, because they continue align not just for frequency but also for amplitude accuracy. So you can hear them go ta 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 ta, going through all of them, and that's basically these guys switching. So you see it in the labs all the time. You know, spectrum analyzers, network are left on all the time, and well, guess what? You're aging them. Anyway, so oh, interesting, very interesting. Take a look at this. This mesh is was sitting here. And this is most likely to make a very good contact between this plate and the chassis here, because these surfaces are smooth, and I imagine that that's what they have this here. Interesting. And look, there is an extra hole that will line up where the pin of the coax enters the unit, perhaps not to disturb the impedance. Interesting. Very cool. Anyway, this is quite, you can see how expensive these things are, obviously all assembled by hand and so on and on. So now we can take this one apart as well. Well, I'm gonna do this off camera. I'm not gonna bore you guys taking screws off. And similar story here, we're seeing exactly the same thing. Obviously there is some PCB in there where all these going. We can already see some mechanical components, very bulky, quite heavy actually. So now we can go and take it off. I think this thing can slide off, but before I do that, let's take these two screws off and see if we can figure out what's going on. All right, there we go. Take this nut off as well. And what do we have here? Oh, come on. There's like 20 more screws. I'll be back. Alright, almost there. Here's the last one. Now, sometimes these guys actually use even ceramic to implement the RF circuits because, well, no expense, you know, is spared in the cases of these, and you want a good electric material, low loss electric material. Let me slide this guy off. And take a look. Yeah, there it is. There's one section, two section, then there is a third section. There we go. Those are definitely our relays, and the contacts should be here. Oh, look at that. Oh no, interesting. One of them is ceramic, but the other two are glass. Wow, they really didn't really, you know, spare any expense. Look at that. Glass substrate resistors for the attenuators, and this one is ceramic. Very interesting. So this is clearly 3-section, so you can see the SMA coming in. These are completely bidirectional, of course. There's no difference between the ports there. There is a, well, I shouldn't say there's no difference. The difference is that in one direction you see the highest or the lowest attenuation, but as you can see, what it appears is that they have put the 10 and the 20, or the 20 and the 10 attenuators on the outside and the largest attenuation in the middle. And this way you have at least fairly close at first resistance attenuation that you see on both sides. This is at least my quick observation here. Now the ground, as you can see, the ground connection directly over there. And we're going to look at this probably under the microscope. And the signal coming in has to couple from here to this gold pad, go through the attenuation or not go through the attenuation. So either goes through or bypasses it. Goes through or bypasses, and the same as that. So if it bypasses all of them, then you have nothing. Ideally nothing. You're going to have some attenuation, some insertion loss, but let's say that would be, you know, it's very small. So it should be 0 dB from here to here, or going through 1, and then, you know, binary selecting at 000, 001, and so on, in order to get 10, 20, 30, 40, all the way to 70 dB of attenuation. So these are defined the sections that are used. This is a 3-section one, and very interesting to see that we have these pins directly on the same chassis here. Now, based on this, it means that there has to be some mechanical way of switching these attenuators in and out. And that should be pretty interesting, and that definitely is all handled here. So let's look at first from the top, so we can see the points. And yep, there they are. These guys are moving essentially. These are movable parts, and depending on the positions of the relays, either you touch them together or you touch them to the attenuator. So remember, this is the first section, this is the second section, this is the third section. Now it's not very clear until I manually move this. And if I can figure out how to move the relay manually, I think I know how to do that. Here we go. So I'm going to move the middle one up. Actually, you know what? Let me move the first one up so you can see what happens. Are we ready? You see that? That selects the attenuator. Now these two pins are going to touch the two sides of that glass piece. So now the signal coming from here, goes through the attenuator, back, down, and forward. But if the relay is in the other position, if I can put it back this way, and if I go this way, you can see how it bypasses it. So this is selecting the attenuation, and this is bypassing the attenuation directly through that piece that's there. Very interesting. And now let's take a look at here. There's a, oops, there goes that. There's a coil in here, which is difficult to see, but that coil, I wonder if we can take this apart further without having to, oh yeah, I think we might be able to. So that coil is obviously going to go move up and down. Now there is no smart circuitry in here, so there's no diodes or anything like that. There's no H-bridge driver, so this is accomplished mechanically. Check it out. This pin separates these two contacts. So when it's in this position, these two get disconnected from each other and those two get connected to each other. And it moves down, another pin separates them. And you may ask, well, this pin is metal. It is, but it actually is coated in plastic. I can feel that when I'm touching it, that this is has got a non-conductive plastic sleeve over it. So when it goes in between these two pins, it actually separates them, changing the direction of the current flowing through the coil, allowing it to now, by applying it, to move it the other way. This is like a solenoid. And the solenoid moving up and down, the direction is handled by selecting this. Very cool. Either the direction is handled by this, or the whichever pin you need to apply a signal to is changing depending on which way it's been turned on and off. And this must be some standard that they're following with regards to the drivers they're using. But this is very interesting, and you can see, let me just move this again just in case you missed it. Here we go. You can see this is how we select the attenuator. This is how we release that piece. And that goes in conjunction with going across here or making it through, skipping this alone. So right now this is skipping it by going through that center piece, which is a direct short, and not going through the resistors that are here, which are the attenuators. Very, very neat. And I'm very curious now, how would the other one look, and if it will have a similar structure as this one. I am curious in taking it apart further, but really there's not much else to look at. It's a very simple structure, and then basically a solenoid. So all the stuff here is low frequency. All the stuff here is low frequency. The RF is handled through these ones. So now you can see why this would age, right? Because these guys keep moving up and down. They're continuously flexing. The amount of pressure these are putting on those glass substrates are going to change over time. Oxidization may happen and so on, and eventually they won't have as much repeatability. But these have obviously infinite linearity and can handle a lot of power. But now, this one, I'm curious to see how it's constructed. Now, you would probably find something like this, you know, let's say in the EXA, for example, this one would have one of these. Or this one, I believe this one has the option for a mechanical attenuator, and this one would have another one, but this is only 6 gigahertz, this is 26.5 gigahertz. So that one is going to have one of these attenuators similar to this one. So yeah, pretty neat. So let's go ahead and take this one apart. I won't bore you with the disassembly again. Let's take a look what's inside of it. Interesting so far, essentially an identical construction. Here you can see the solenoid coil a little bit better. Interesting different material here, or at least a different, what do you call it, plating on top of it. But yeah, neat. Now we're gonna see, it looks like it's very similar. And I'm not surprised because they don't design these, you know, many times with different frequencies. And that's why they're probably using the glass substrate on the other one, because they don't care. They're just gonna put, you know, whatever connected they need. But this one has to be going, it has to work all the way up to 26.5. Let's see if there is any difference under here. Oh man, this one is even worse. And here we go. Now we will be able to see the construction here. And there you go, see? It is exactly the same. So indeed they don't really care too much about using the components that are rated all the way up to 26.5. But there is one difference between these two, and I'm going to leave it as a puzzle so you can figure it out. I'm not going to say anything, but it's pretty obvious. I've talked about it before. But you can see, interestingly enough, that we have glass and ceramic substrate, or quartz and ceramic substrate, for different types of attenuation. And it's interesting that they're not all made of glass or all made of ceramic. Now this one, it has 4 sections, so it can give you finer resolution in the steps, and the connectors are obviously different. That's not the difference I was referring to. The connectors are type K. Now the coating of this is different. This metal is different, so I'm not sure why. if that would make a difference in terms of frequency response. I don't think so, but otherwise the functions are quite similar. So if I slide this guy out, you will be able to see that indeed we're dealing with, look at that. Interesting. They moved away from, they moved away from using the mechanical switches to decide the direction of the current or the order in which the relays are active, and they've gone fully electronic. That's pretty interesting. Very cool. You see some diodes there, probably to protect for flyback voltages from the switching of the individual relays, but you can see there is the coils very clearly. That is cool. So they have indeed changed their style, and looks like this actually can be easily disassembled. I'm not sure. Oh, I just touched this spring with my hand. Anyway, it doesn't matter. So this now makes actually more sense. It makes sense why this is dead and it doesn't switch, because he has electronics, so they must have damaged, they damaged the switches or damaged these. I wonder what these are, shift registers or something, but if you damage this, it's basically done. That's why I could not switch the relays in this one, but I could switch the relays in the other one, and you can see the difference in style of achieving essentially the same task, because these inputs are standardized. So very cool. Learned something new there, going from the old HP model with a mechanical switching to a completely electronic version of it. So this one, when you turn it on, it must come up in some state, maybe a default 0 dB or something, and then you either load the bits or individually switching the binary combination, and it will automatically figure out which one of these it needs to turn on in which order to give you attenuation. But anyway, I don't want to go into too much details here because it's not that interesting other than understanding the principle of operation. But the construction is quite a bit more complex. But you know what, since we are here, let's take this one step further, since this is a bit easier to open, and let's see how this mechanical section works. It still is pretty interesting to see. Now this is a bit of a destructive disassembly, and you could tell before I even took it apart that it was going to be the case, because if you look over here, the only place where there is flux are on these connections E1, E2, E3 all the way to E11 and E12, which means that this was done at the end of the assembly. So they put this with the coils pins sticking out, and they push this in and then they solder it. So by taking pins out, I destroyed the board. But anyway, this was already not working. But so this is a 50227864 is a part number, Agilent revision 001. It's one of the very first ones they made. Nice, neat, clean. And I'll tell you the part number of this. Sorry, I can't do it on camera because I can't read it. One of them is a 74 VHC123A. All of them are actually. Interesting. There's a bunch of other ICs on there, so there's clearly a bit of a complexity associated with figuring out how to do the switching, but otherwise pretty straightforward. And here now you can have a better idea, and somebody has been meticulously marking these depending on where I guess during the assembly process, but I should be able to move these somehow. Oh man, they're really stuck. There you go. There you go. I just moved one of them down, you can see, and I can move it back up, I'm sure, if I put enough force in it. Come on. There you go. They moved back up. So it's just, again, solenoid, simple, exactly the same style. But we're not going to stop here. Take it further apart. So this was definitely worth taking apart, because it just goes to show how much effort they've gone through this. So these little pins that are plastic have a little nub at the end of them, and those nubs lock onto the copper thin film pieces that make contact with the attenuators, and these guys basically move in and out with the movement of the solenoid, and you can see that I can move them, you see, this way, and that's how those pieces move back and forth, and that's how we can achieve this attenuation. Now this piece can be further taken apart, and that's where the magnet is housed, and you can see individually magnets. I mean, this is just must have taken forever to build, because they're all manually assembled, and you can see I've just gained myself a whole bunch of magnets. If I don't break it, I should be able to take it out. Look at that, little square magnets. Very nice, they're pretty strong. They're not neodymium, I don't think so. But yeah, pretty cool. And you can see now the pendulum effect there, the plunging effect, I should say, of this piece there. Very cool. And that's how obviously the magnetic field underneath here then controls the direction of the current. Will they control it, whether we will stay this way or this way. And there's a latching, which means that you don't need to activate and hold the magnetic field permanently on there. They switch one way and then they switch the other way. So that's pretty cool, and they're all made exactly the same way. all manually assembled. And on this side here we then have all the copper pieces, and this is assembled by pushing it in. If I don't end up bleeding, I should be able to take this out. There we go, like this. And check it out. The little, you see this little slot here? That's where the tip of that piston thing goes in, and then it pulls it down or gets pushed up like this way or this way, and they go through these little holes. It's just so complicated. Oh my god, there's a reason, you know, if this is working, these attenuators are functioning, money, it's going to set you back a couple of $1,000s. So these are not cheap. Now, there we go, we can take this out and we can see, oh, interesting. I wonder why they have this. Maybe it's just for springing. Oh, this is just for creating a bit of a springing action. So the compression, using compression to place it in here so it doesn't move. And yeah, you got this different little seesaw actions. As I pull them down, you can see I locked them in the wrong places. So these got latched to the bottom. As I pull them out, they should all be like this. They should be like this. There we go. Like that. So a bypass would be when both of these are down. This would be a bypass when this and this touch here and here, and when they're pushing up, they will be touching the both sides of one of these guys. There you go. Now hopefully it's very clear how these things function and how they're built. And this entire piece here maintains a 50 ohm characteristic impedance. So it's a complex, I wouldn't say it's not really a coplanar and it's not really a microstrip. It's almost like a coax because it is embedded in here where it is surrounded by ground on all sides. So it's almost like a coax piece. And yeah, pretty neat. And obviously none of these circuitry is high speed, of course not. And you can see the style of this one being quite a bit different, but really using the same relays. You can see the same magnet here, same coil there, same pins going through, soldered afterwards over here. It's just that the connections are redone by mechanics as opposed to by electronics. So yeah, very cool. Now, what did I say I wanted to do? Oh yeah, I wanted to also very briefly show you one of these guys under the microscope, so you can see the individual little printed resistors on there, or deposited resistors on there, and that makes up the attenuators. So let's take a quick look at that. And here we are. Now we can take a look at it under the microscope. I'm sorry I'm filming the screen. I just want to quickly show you this. So this is the piece, one of the ones that has the glass or the quartz substrate, and you can see very clearly the structure is really quite straightforward. Now these are the ground connections, and these ground connections are vital because these ground connections have to be an RF ground as well as a DC ground, because this is DC coupled, the whole system. So this attenuator works from DC. And you can see this is the input output, doesn't matter, it's fully reciprocal. Now here you can see this little line over this from the contact of those copper films coming in contact and releasing. This was used quite a bit. And so you can see when it makes a contact, there makes a good conductivity there. These are gold plated, and this is a printed resistor network. So you have, you know, parallel R series R, parallel R series R, and this is creates the, you know, desired attenuation depending on how many sections there are and how you choose the values of the resistor. And this is quite a simple design because you have to maintain a 50 ohm environment. And you have to make sure that the impedance looking in here is 50, impedance looking there is in 50, all the way through the range of the frequencies that you want. And that's one of the reasons they use the quartz substrate here, is because it makes it quite a bit easier. And what I was saying in terms of the fact that this is elevated from the bottom, so it kind of behaves like a little tiny coax with all the films going right through, all the little copper films going through it. So you can get an idea of the structure of how it looks like. It's a pretty neat and pretty straightforward design. Anyway, I wanted to show you what it looks like. So for the sake of completion, I hope you enjoyed this little quick video here, you know, as I'm doing cleaning around the lab and find a little thing that I want to show you. It's a more of an ad hoc video because I'm just, you know, making things, observing, and I'm telling you as I go along. I hope you enjoyed it, and I'll see you soon.